Okay, so exam time is right around the corner, and that means we need a good, solid review. Today, we're going to blast through the absolute must-knows, the key data structures that are pretty much the building blocks of all computer science. Let's just dive right in.
You ever wonder about that? Seriously. You click the back button and boom, you're on the last page. It feels totally instant, almost like magic. Well, it's not. It's a very specific, very clever data structure doing all the work. And by the time we're done here, you'll know exactly which one it is and why it works so well.
All right, here's the plan. We're going to start with the foundations, arrays and lists. Then we'll dive into the rules of order with stacks versus queues. After that, we'll see how to connect nodes with linked lists, learn to navigate a binary tree, and we'll wrap it all up with the one built for pure speed, hash tables. Sound good? Let's go.
Okay, first things first. You gotta know the basics. You can't build a skyscraper without a solid foundation, and you really can't build good software without understanding these fundamental structures.
So what you're seeing here is a classic trade-off. Think of an array as being super organized but kinda rigid. All its elements are the same type and they live right next to each other in memory. That makes grabbing any one of them lightning fast. A list, on the other hand, is all about flexibility. Its items can be scattered all over the place in memory, and they can be different types. But that freedom has a small price. It can be a bit slower to find things. The bottom line? Use arrays when you need speed and you know what you're dealing with. Go for lists when you need that flexibility. And then there's this guy, the tuple. It seems a lot like a list at first glance, but it's got this one non-negotiable rule: it is immutable. That's a fancy way of saying once you make it, you cannot change it. Ever. No adding things, no removing things, it's locked in. So why would you use it? Well, it's perfect for data you absolutely do not want to be changed by accident somewhere in your code.
So we just looked at structures based on how data is stored. Now let's switch gears and look at two that are all about the rules for how you access that data. Get ready for stacks and queues.
Honestly, this slide says it all. A stack is LIFO, last in, first out. The analogy is perfect. Think about a stack of dinner plates. The last one you put on top is always the first one you grab. A queue is the complete opposite. It's FIFO, first in, first out. And yeah, it's exactly like a line at the store. The first person to get in line is the first person to get helped. It's all about being fair.
And there it is, the answer to our big question from the beginning. Your browser's back button? It's a stack. Every single time you go to a new website, that page's address gets pushed onto the top of the stack. When you hit back, the browser just pops the most recent page off the top, and it reveals the one that was right underneath it. So simple, but so effective. Same thing with undo in a text editor.
Let's just watch it happen. We start empty, we push item A onto the stack. Easy enough. Then we push B. And notice it goes right on top of A. Now here's the key part. When we pop, which one comes off? B, of course. The last one in is the first one out. That leaves only A in the stack. It's always about what's on top. Now let's flip that and look at a queue. We enqueue task 1, then we enqueue task 2, and it goes in line behind task 1. But see what happens when we dequeue. We don't touch the last item. Nope, we take from the front. Task 1 gets processed and removed, leaving Task 2 to move up to the front of the line. It's just like a printer queue. First come, first served.
Oh, and here's a quick pro tip on queues, the circular queue. See, with a regular queue, once you take an item from the front, that memory slot just sits there, empty and wasted. A circular queue is way smarter. It basically treats the end of the line as being connected to the beginning. So when it reaches the end, it just loops back around to fill in any of those empty spots at the front. It's just a much more efficient use of memory.
Okay, so up until now, everything we've looked at has been stored together, like in a block. But what if we built a list based on connections, where each item just knows where the next one is? Well, that's the whole idea behind a linked list. The building block of a linked list is called a node, and every single node has two jobs. First, it holds the actual data, the value we care about. Second, it holds a pointer. Think of a pointer as just an arrow or an address that points directly to the next node in the chain. It's like a treasure hunt where each clue tells you exactly where to find the next one.
This is where linked lists really shine. If you want to add something to an array, you might have to shift a whole bunch of elements around to make room. It's a pain. With a linked list, you can just drop your new node anywhere there's free memory. Then, all you do is a tiny bit of rewiring. You tell the node before it to point to your new node, and you tell your new node to point to whatever came after it. It's like a quick, clean, surgical operation.
All right,
Let's graduate from a simple chain to something with a little more structure, a branching hierarchy. That's a binary tree. It organizes data in a really useful way, but you have to know how to navigate it, or traverse it, to get anything done.
When it comes to visiting every single node in a tree, there are really three main ways to do it. We've got pre-order, in-order, and post-order. And the only real difference between them is when you decide to visit the root node compared to its children.
Pre-order is easy to remember. Root, left, right. You deal with the node you're currently at first, then you explore its entire left side, and only after you've done all of that do you explore its entire right side.
So, if we use that root left-right rule on a sample tree, this is what the output would look like. We'd start at the top, say at number 15, and process it. Then, we'd go all the way down the left branch, following that same rule before we ever even touched the right branch.
Now for in-order, we just shuffle the rule. It becomes left, root, right. So this time, you go all the way to the bottom left first, then you process the root node in the middle, and then you go down the entire right side.
And would you look at that? When we apply the in-order rule to a properly sorted binary tree, what do we get? The numbers come out in perfect sorted numerical order. This is not a coincidence, folks. This is a fundamental property of in-order traversal, and it's a huge thing to remember for any exam.
And our last one is post-order. You can probably guess the pattern now. It's left, right, root. With this one, you explore all of a node's children on both sides before you ever process the node itself. You're always saving the root for the very end.
We've saved the speed demon for last. Our final stop is the data structure that is built for one thing and one thing only: insane speed. If you need to find a piece of data right now without searching, you need a hash table.
So the magic behind a hash table is something called a hash function. It's just a special formula that takes your data, does a quick calculation, and tells you the exact memory address where it should be stored. No searching needed. But what happens if the formula gives the same address for two different items? That's called a collision. The simplest way to handle it is just to put the item in the next available slot. If that one's taken, you try the next one, and so on until you find an empty spot.
And that wraps up our review. From the flexibility of lists, to the strict rules of stacks, to the pure speed of hash tables, every single one of these structures is a tool for a specific job. So I'll leave you with this question to think about. When you're solving a problem, think beyond just how fast it is or how much memory it uses. Ask yourself, when does the sequence, the history, the order of the data become the most important thing? When you can answer that, you'll always know which data structure to choose.